Okay, so in this video, I would like to run through the objectives for this week. And so the objectives are concerning the sections 12.5, 12.6, and 12.7. So I recommend kind of having the book open as you're working through them and kind of, taking note of what you're using from the book to help you solve the problems. And then you can kind of keep that material at hand for when you're doing your tests and stuff, and you can highlight things within the book or whatever is your preferred method of making sure you can identify that material quickly. So the first section is all about collision theory, which is where we're going to be using the Arrhenius equation to see how activation energy and frequency factor along with temperature, affect the rate constant and the rate of the reaction. And then the second section is about reaction mechanisms, which can be a little bit tricky, and we introduce the idea of an elementary reaction, or sometimes it's called an elementary step. And then finally, there's a really short section on catalysis, which is pretty easy going. So let's hop in and have a look. So this is simply about interpreting a reaction energy diagram. So there are a few things that we're always kind of looking for here, and that one of the big ones is your reaction exothermic or endothermic? You want to be getting that right consistently. And then just kind of identifying the activation energy for your reaction is another big thing, knowing what that means. And then also it sounds really dumb, but reading the scale correctly is often important for these types of problems. So how we always write an energy diagram, we always have reactants on the left, products on the right, just like a balanced chemical equation. And then the difference in energy between your reactants and your products, that's called the enthalpy of the reaction. And the difference in energy between your reactants and the transition state here, so this point here is called your transition state, and that there is your energy of activation for the forward reaction. And of course, if you do the difference in energy between the products and the transitionary state, that's your energy of activation for the reverse reaction. So, like I said, a lot of this is about reading the scale correctly. So the first question that they're going to ask you is, what is the heat of the reaction? So in this reaction, we know that energy is released because the products are at lower energy than the reactants, right? The products are down here at 50 kilojoules, and the reactants are at 200 kilojoules. So it goes from 200 kilojoules down to 50. So what does that mean? That means that there was a loss of 150 kilojoules, right? A loss of 150 kilojoules, minus 150 kilojoules per mole of energy was released. So, so what's happening here is that this is what we call a exothermic reaction. Energy is released as the reactants are converted into products. We're also generating heat. Heat is going to be released. All right. So can I determine the activation energy? Yeah, you just got to read it off the scale, right? So yes, if I have a labeled energy diagram, I can always get the activation energy. So what is the activation energy? I have to go from 200 kilojoules per mole all the way up to 300, 350. So the activation energy is 150 kilojoules per mole. All right, so that's it. So I can determine the activation energy. It's 150 kilojoules per mole. Now, can I determine the activation energy of the reverse reaction? Of course I can. I've got an accurate energy diagram that is labeled with all of the energies. So to get to the transition state going in the reverse direction, I've got to go from 50 all the way up to 350, 50 up to 350. So hopefully you agree that that is 300. So what does this really mean for us? Well, the lower the activation energy, the faster the reaction. So this means that the forward reaction will be quicker than the reverse reaction. Okay, so that's kind of interesting. All right, let's have a look at this. It says relating activation energy to reaction rate. Oh, there you go, right? I just said it. So these things are inversely related. So if you remember, it is that, well, let's put it this way. K is equal to AE to the minus EA on RT. And what that really means is that K goes down as EA gets bigger, right? So as your activation energy gets bigger, your K goes down. What do we know about rates of chemical reactions? Rate is always equal to K multiplied by a bunch of concentration terms, isn't it, right? So what it's also really saying is that as K goes down, rate goes down. So another way of saying this is that as activation energy goes up, rate goes down, right? Now, that's it. So if everything else is constant, as the activation energy goes up, the rate of the reaction goes down, and that's the key information here. So let's see what we've got in here. Suppose a pair of chemical compounds A and B can react in two different ways. A plus B gives C. That would be under one kind of set of conditions. And then A plus B gives D, and that would be under a different set of conditions. And this happens all the time, right? That things, depending on the conditions, when they react, produce different products. So if you mix sugar and oxygen together at room temperature, nothing much happens. If you mix sugar and oxygen together at a very high temperature, then they're going to turn into carbon dioxide and water. So this is both reactions are exothermic, but the heat of reaction number 2 is larger. So let's think about this. We've got, for number 1, here's energy. So we got A and B are our reactants, and it says both of the reactions are exothermic. So our products for number 1 were C, right? Okay, and they're like relatively close to one another, right? The exothermic, the products still lie lower in energy than the reactants, which is what makes the reaction exothermic. But here is the second one, and we've got a bigger gap in energy, you see, right? And it's a pretty small gap in energy, delta H. Okay, so that doesn't really mean much, right? Okay, that doesn't really mean much. It says, so the heat of reaction number 2 is larger, so that means that there's just a bigger gap between the products and the reactants. If a reaction vessel is charged or filled with A and B, then at first D is produced faster than C. So that means that the rate constant for D is a bigger number than the rate constant for C. So use these facts to sketch a qualitative reaction energy diagram for both reactions. I knew it. So what we're really saying is that the second one, because it goes faster, has a bigger rate constant. That means that for the reaction that produces D, the activation energy is lower. So what we want is this. We want a big, tall activation energy for the first one, and then we want a short activation energy for the second one. So we got to get a couple of things right, yeah? They have to both be exothermic. Delta H for reaction 2 has to be bigger than delta H for reaction 1. And then the next thing, because reaction 2 goes faster than reaction 1, the activation energy for reaction 2 has to be less than the activation energy for reaction 1. So hopefully I've kind of tried to illustrate that for you. Okay, so not too bad. Okay, so in this problem, we're looking at the qualitative predictions of the Arrhenius equation. So we should write out the Arrhenius equation. The Arrhenius equation is written like so. It says that K is equal to A, E minus EA on RT. Now there are some other common rearrangements of the Arrhenius equation. We can put this in the linear form, where we have like the slope-intercept form, and we can also write it in what's called the two-point form of the Arrhenius equation, and they can be helpful when solving certain kinds of problems. But let's just look at the standard form of the Arrhenius equation and see what it's telling us. So K is your rate constant, and what we know is that as the rate constant gets bigger, your reaction goes faster. A is what we call the frequency factor. The frequency factor is a measure of the likelihood of your reactants coming together with the correct orientation. So if you have super complicated reactants that have to align just so, then your frequency factor is going to be pretty low. If you have really simple molecules that when they collide, there's a very high probability that everything is oriented in the correct orientation, then your frequency factor is going to be big. Okay, and so now we've got some terms that we've seen before. EA is your activation energy, the energy needed to get to the transition state. And it needs to be given in joules per mole. Often in the problem, it's stated in kilojoules per mole. T is your temperature in Kelvin. And then so that we end up with a unitless term for the exponent there, R is the ideal gas constant, but it has to be given with units of joules per mole per degree Kelvin, so it has a value of 8.314. So when we put all of this together, what does it mean? Well, it means that as your frequency factor gets bigger, K will get bigger and your reaction will go faster. It means that as your temperature goes up, the exponent in the second term will get smaller, and because it's a negative exponent, all of these quantities, by the way, are positive numbers, K will also get bigger. The activation energy, as that increases, this negative term here will get bigger, therefore K will get smaller. It's important to recognize that there is an exponential dependence of the temperature on K. So that means that relatively small changes in temperature lead to big changes in K. And similarly, there is an exponential dependence on the activation energy. So relatively small changes in activation energy lead to big changes in K, and we'll get to that in a moment. So let's put all of that together to qualitatively describe what will happen here. Suppose the concentration of all reactants is kept the same, but the temperature is lowered by 5%. How will the rate of the reaction change? So lower the temperature, the reaction will slow down. Because there's an exponential dependence on the temperature and reaction rate, it will slow down by more than 5%, right? Small changes in T or EA lead to big changes in reaction rate. So now we have the second part of the problem. It says, suppose the concentrations of all reactants is kept the same, but a catalyst is added. So catalyst doesn't change anything other than the activation energy. Doesn't, for example, change the enthalpy of the reaction, which has the effect of lowering the activation energy. So it's going to go faster. So the reaction will speed up. It lowers the activation by 10%, so it's going to be speed up by more than 10%. All right, if you want to be exact. All right, so a little word of warning here. Don't claim that something is exponentially dependent on something else unless it's kind of this form, in science class at least. Often in like everyday language, if we mean that something is like highly sensitive or changing rapidly, we say there's, it's exponential change. But in science and math, it has a very, very specific meaning. And in this case, our y is our k, isn't it? And then we're saying it has an exponential dependence on the temperature and the activation energy. So you want to be a little bit cautious with using those terms in science and math class. All right. Using the Arrhenius equation to calculate K at one temperature from K at another. Now this is where you want to get your 2-point form of the Arrhenius equation out. So log K1 on K2 is equal to minus EA on R multiplied by 1 on T1 minus 1 on T2. And in our case, it looks like what we're going to have is everything except for one of the K's, right? Because we're trying to calculate a K. So we're going to have 1 K, 2 temperatures, and an activation energy. Remember what I said, that we need to make sure that we have our temperatures in Kelvin and our activation energy in joules, and then also that we use R is the correct value of 8.314 joules per mole per degree Kelvin. So if you write your units out for your R, it kind of reminds you of the units for everything else. The other thing that sometimes is forgotten is that minus sign at the front of the right-hand side there. Now, what I'm going to do is I'm actually going to use my calculator to solve for this, but you can also use an online equation solver like Wolfram Alpha or something like that. Okay, so the rate constant of a certain reaction is known to obey the Arrhenius equation. Well, that's convenient, and to have an activation energy of 63 kilojoules per mole. So let's write that down. EA equals 63 times 10 to the 3 joules per mole. I just replaced the kilo with times 10 to the 3. Okay. And the rate constant of this reaction is 2 by 10 to the 2, so 200, right? 2 by 10 to the 2 at a temperature of 154. So 154 plus 273.15. Let's just calculate that now. Got to turn that into Kelvin. 154 plus 273.15 equals 427.15 Kelvin. Okay. There we go. So we got the rate constant at one temperature. So we know what we're going to be, what is the rate constant at 71. So that's what we're solving for there. So 71 plus 273.15. Let's calculate that. 71 plus 273.15. Enter. 344.15. Okay. So looks like I got everything, and then I'm ready to roll, right? So I just got to write my numbers in. I'm solving for K2. So log K1 2 by 10 to the 2 over K2. I'm just going to put that as X. That's going to be my X that I'm going to solve for. Equals minus the activation energy, 63 by 10 to the 3, over R, which is 8.314, multiplied by 1 on T1, 427.15, minus 1 on T2, 344.15. 8.15. Now, the important thing here to recognize is that the temperature went down, so K2 is going to be less than K1. And remember, it's an exponential dependence on the temperature. So it's going to go down a lot. All right. So this is my expression here. I'm going to do a weird thing. I'm going to reorganize it so it equals 0. So all I'm going to do is subtract that term, that minus 63 by 10 to the 3 on 8.314 times all of that thing. I'm just going to subtract that from both sides. So it's going to be this. And the only reason I'm doing that is because it's going to make this whole thing equal 0. And my reasoning for doing that is just because that's how my calculator works. All right, there's not really any other major reason for that. All right, let me just bring this over so we have a bit more space for my calculator. Put my calculator over there. All right, so what I'm going to do is I'm going to use the solver in the calculator. And if you don't know where it is, you go Math, and then if you go up 1, you'll go to Solver. Okay, and then on the top line here, I'm going to put my formula, and you can see that my solver is set up that you always put your formula in so it equals 0. So it's going to be log 2 by 10 to the 2 on, and then here's the x button, x, that's what I'm solving for, plus 63, I somehow reason I wrote 6.3, 63 by 10 to the 3, so 63 kilojoules per mole on R 8.314 multiplied by 1 on T1, 1 on 427.15 minus 1 on T2, which is 344.15. Close my parentheses, enter. Now on the next line, I have to put a guess in for X. It was 200. Now I lowered the temperature a lot, so I'm going to say that it's 5. And so with the cursor sitting on the line where I put my guess in, I ask it to solve. And so now I go alpha, and then that activates the green options, solve. And there it is. Now it's a little hard to read, so I'm going to quit out of here. And then I'm just going to ask the calculator to tell me what X is, because that's what we just solved for. And so X is 2.77. There we go. So my new rate constant, K2, is 2.77. And so that's cool because I changed my temperature by, I reduced my temperature by, let's have a look, 4, so my temperature got dropped by 19.4%, right? It went down to 80% of what it was, so it got dropped by about 20%. But then my rate constant dropped by a lot more than 20%, right? So you can see my rate constant dropped by, well, it's only 1.3 or 1.4% of what it was previously. So that means it dropped by over 98%, right? So you see the effect. Small change in temperature, big change in the rate constant. All right, so that's it, and using the solver. Now, if you don't like using the solver on your calculator, you can use the solver in Wolfram Alpha, which is really easy. You just put the expression in. You don't have to do this rearranging so it equals 0. You hit the button and it tells you what X is. All right, that's good, I hope. Okay, so this problem here is similar, but we're going to calculate EA given K at multiple temperatures. Now there would be a couple of ways of tackling this. One is you could make a plot of log K against 1 on the temperature, and that would give you a line where the slope was equal to minus EA on R. That'd be pretty complicated to do. You could use the linear regression feature in your calculator if you really wanted to speed that up and you were determined to do that way. But we do have 2 points here, and I think the easier way would just be to use the 2-point form of the Arrhenius equation like we used in the last question. So that would be log K1, K2 equals minus EA on R, 1 on T1 minus 1 on T2. So this is my favorite form of the equation, to be honest, when I'm trying to solve for something. The only thing you obviously can't solve for when you're using that form of the equation is the frequency factor, because it just doesn't appear there. But otherwise, if you're solving for a K, a T, or an activation energy, it works pretty good. So I'm thinking we are good to go here. Our temperatures are going to need to be converted to Kelvin though, right? Because they are given in Celsius. So as long as we do that, we should be okay. So let's just kind of make sure we can get everything listed out okay. And then we put our numbers in and we'll solve. So R obviously 8.314 joules per mole per degree Kelvin. I like to state that first. It reminds me of what my units are going to be. K1, 1.4 by 10 to the 9. T1, 354 plus 273.15. We'll calculate that in a moment. K2, 2 by 10 to the 8, so it must be at a lower temperature. T2 equals 215 plus 273.15. So there we go. All right, so let's get our temperatures in Kelvin. And then I think we've got everything and we're ready to roll. So let's just put those guys in. Here we go. 354 plus 273.15. Enter. 627.15. And finally, 215 plus 273.15 equals 488.15. So that's looking pretty good. So remember, I'm just going to reorganize this so that it equals 0. So it's just going to be log K1 on K2 plus EA, which I'm going to put in as my X, R, 1 on T1 minus 1 on T2 equals 0. And so now away I go, and I've just got to make sure that I don't accidentally put any of the wrong numbers in. So math, go up 1 will allow me to get to solver. Set solver, go to the top line there, clear my equation, and let's start putting stuff in. Log of K1, 1.4 by 10 to the 9, divide by K2, 2 by 10 to the 8, close parentheses, plus EA, which is my X, on R, which is 8.314, multiplied by 1 on T1, which is 627.15, minus 1 on T2, which is 488.15. Close parentheses, hit enter. Now I'm going to put a guess in for my X. So remember, this is going to return the activation energy in joules. Typical activation energies are a few kilojoules, so why don't we just put in 5,000? And activation energies are always positive numbers. So now I'm going to solve alpha, solve. And then I'm going to quit out of here, and I'm going to ask the calculator to display X so I can actually see it. And there it is. Now I want to remember that this is in joules. So it says round your answer to 2 significant figures. Doesn't say for any particular units. It doesn't say it has to be in kilojoules, right? So 3.6 by 10 to the 4 joules per mole. There we go. And that's fine. Okay, now if you wanted to, you could write it as 36 kilojoules per mole, and that's a reasonable activation energy. Okay, cool. Now if you got a negative number, you'd know you were wrong. So sometimes the solver will be like, it won't give you a, it'll say it couldn't solve. And sometimes that's because there's two possible answers. So for example, you probably know this when you solve a quadratic, you can get two roots, right? What you can do is put bounds in. And so we could set the lower bound in this case to be 0 because we know that our x has to be a positive number. So that would be one way if it returned an error, something that you could try. You go alpha, solve, and then it'll only look for positive numbers, and it worked out just fine. All right. Okay. Not too bad. Okay, so in this problem, we're asked to identify the molecularity of an elementary reaction. And that's pretty easy. All we have to do is add up how many moles of reactants are present in our elementary reaction, and then kind of transfer that into the language of molecularity. So if there's one species involved, 1 mole of stuff involved, it's going to be unimolecular. 2, it will be bimolecular. 3, it will be termomolecular, and if there are 4, quadrimolecular. So it should be pretty simple, and as long as we have got an elementary reaction, cannot be determined won't be an option as far as I can tell, but let's see what we've got. So this has got 2 moles of reactant here, so it is bimolecular. This has got just the 1, so it is unimolecular, and this has got 1 plus 2, that equals 3, so that is termomolecular. So that's pretty straightforward. Now, this is kind of like beginning to get used to some terminology so that later on we can work on reaction mechanisms, which is quite complicated. So in this problem, we're asked to talk about or asked to identify intermediates. So intermediates are things that are created along the way in a reaction mechanism, but don't appear in our overall equation. So what we have to do is we have to add together the components that are present in our elementary steps, and we're going to see to get an overall equation, and we're going to see what cancels out. So let's have a look. And those things that cancel out, those things that are made along the way but don't actually appear in our overall equation, they're our intermediates. And I think I've just found one. So we're going to add them together, these elementary steps, in a style similar to how we add together half equations when we're balancing redox equations, or when we're adding together equations and we're doing things like Hess's law. So here we go. And like I said, I think what I found that's going to cancel out, what you're looking for are things that appear in both the products and the reactants in different steps, right? So I think I found some. So first of all, one of these BRs is going to cancel out. That's made, one of those that's made in the first step, and then the second BR is also going to cancel out there. So there looks like we've got one intermediate BR there, and then the other thing, it looks like this chlorine here, this atomic chlorine, is also going to cancel out. So there we go. So we've got Br2 plus OCl2, and the whole of the last one cancels out, gives nothing there, and then that's going to be BrOCl plus BrCl. There we go. So that looks good. You always want to check that your overall balances. So we've got 2 bromine, 1, 2 bromine, that looks good. I've got 1 oxygen, 1 oxygen, that looks good. I've got 2 chlorines, 1, 2 chlorines. So my overall equation balances, and I was right. The things that are made along the way that are not in my final equation are atomic bromine and atomic chlorine. So let's just answer this. So here's our question here. Write the chemical equation of the overall reaction. That's this guy there. We got that done. Are there any intermediates? The answer is yes. If there are intermediates, write down their chemical formulas. Put a comma between each. So it would be Br, Cl. Remember, we just want the identity, so we don't put any numbers out the front. You wouldn't put, for example, 2Br. We were just giving the identity of the intermediate. Okay. Write the rate law for the following elementary reaction. Use K1 to stand for the rate constant. So what's important is that only for an elementary reaction, you can't ever do this for an overall or a balanced chemical equation, the order of your reactants is just equal to the stoichiometric coefficient. So this will be rate equals K1, because it said use K1 for the rate constant, and then it's going to be the concentration of O3, and you can either put to the power of 1 or you can just leave that out. Normally we would just leave it out, so rate would be equal to the concentration of O3, which is ozone. There we go. Okay, so you'll see a lot of balanced chemical equations, or a lot of examples given that are concerning gases found in the atmosphere, like ozone and stuff, because that's been an interest of chemists who are trying to solve problems like ozone depletion and global warming issues. So that's been a really big focus in chemistry. In fact, people won the Nobel Prize for figuring out why the ozone layer was developing a hole in it using the principles of atmospheric chemistry. Okay, writing the rate law implied by a simple mechanism with an initial slow step. So there are really kind of two types of problems where you have to figure out the rate law from a mechanism. The first one is the easiest, and that's where the first step is slow. And the second type of problem is more challenging, and that is where the second step is slow. So you should know how to do both types of problems and feel comfortable with that. So suppose the reaction between nitric oxide and bromine proceeds by the following mechanism. So there's two elementary reactions with their own rate constants. And then here's the information that you need. It says suppose also K1 is a lot less than K2. That is, the first step is much slower than the second. So the first step is what we call the rate determining step, and the rate law for the rate determining step is equal to the rate law for the reaction. Okay, because the second step goes so quick, it doesn't really slow it down at all. Okay, so that's what we want to keep in mind. Now, because step 1 is an elementary reaction, we can get the order of the coefficient of the reactants in its rate law just from the elementary reaction stoichiometric coefficients. So I know that for step 1, the rate of that step will be equal to K1, the rate constant, multiplied by the concentration of NO, multiplied by the concentration of Br2, because there are one of each of those things in that elementary reaction. And that is also equal to the rate for the overall reaction, because step 1 is the rate determining step. So let's go on here and see what we've got. So it says, write the balanced chemical equation for the overall reaction. So we've got to add together the two steps and eliminate any intermediates. And it looks like our NOBr2 is going to be our intermediate, doesn't it? Okay. There we go. So that's going to cancel, that's going to cancel, and what we're left with is 2NO plus Br2 gives 2NOBr as my overall reaction. Now, what I know is that the rate overall is going to have a rate law it's like this. It's like K overall multiplied by NO to some power A multiplied by Br2 to some power B. And so, you know, that's just like we would normally have for a reaction. The question is, can I figure out what A is, can I figure out what B is, and can I figure out what K overall is? Well, I can, because I know that my rate overall is just equal to that. So what is that really telling me? It's telling me that A equals 1, B equals 1, and the overall rate constant is exactly the same as the rate constant for the first step. Alright, so let's see what we got here. It says, write the experimentally observed rate law for the overall reaction. And then it gives you a warning. It says that your answer should not contain the concentration of any intermediate. So K multiplied by NO multiplied by Br2, both to the power of 1. So when you have a slow first step, when the initial step is slow, it's pretty easy. Right? It gets more complicated when the second step is slow, and we'll work through that now. We're going to kind of slowly build up to being able to do that type of problem. So to be able to do that second type of problem, one of the key concepts is to be able to express the concentration of an intermediate in terms of reactant concentrations. So hopefully you see what I mean here. So it says, consider the following elementary reaction, and it looks like it's a decomposition reaction, right? So we've got this compound here, breaks apart to give this cation and this anion, and this is an elementary reaction, right? So what that means is that I could get the rate law for this if I wanted to, because I know that there's only one of this compound here, so the rate would just be something like rate equals K, and then I'm just going to call, here we go, CH3, 3CBr, and that would be first order because there's only one of them in that elementary reaction. Now the stoichiometric coefficient is equal to the order only for an elementary reaction. All right. Now this reaction is interesting. It's what we call a reversible reaction. So the reverse reaction can occur simultaneously as the forward reaction. That is, these two things can combine to reform the reactant. All right. Now there's a state in chemistry called equilibrium, and in an equilibrium state, the rate of the forward reaction equals the rate of the reverse reaction. Right? So what that actually means is that overall there is no change in concentration. So it's kind of like, you know, if you think about your bank account, you know, if money is going in as fast as money is coming out, then the balance never changes. Right? Okay. So in this situation where we talk about things being in equilibrium, we're saying that the products are being formed just as quickly as the products are being converted back into the reactants. So what that means is that the rate of the forward reaction, we're going to call it rate 1, is equal to the rate of the reverse reaction, which we're going to call the negative of 1. Now we already know that the rate of 1 is equal to K1 multiplied by the concentration of our reactant to the power of 1. So what about the reverse reaction? Rate, what we're going to call a minus 1. Well, that's equal to K minus 1 multiplied by the concentration of each of these two ions to the power of 1. So these two things here are equal, right? Because the rate of the forward reaction equals the rate of the reverse reaction. So K1 multiplied by the concentration of CH3 3CBr is equal to K minus 1 multiplied by the concentration of CH3 3C plus times by Br minus, right? So yeah, that's what we know. So so that's an interesting thing. That's a consequence of the rate of the forward reaction equaling the rate of the reverse reaction. So now let's have a look at what they ask for in the problem. It says write an expression that gives the equilibrium concentration of this guy, this cation here, in terms of K1, K minus 1, and the equilibrium concentrations of the other two things there, the anion and the reactant. Well, that's going to be pretty easy, isn't it? I've just got to divide both sides by K minus 1 and Br minus. So it's going to be K1 on K minus 1 multiplied by Br minus times by CH3 CBr, and then that's going to be equal to the concentration of the thing that we're interested in. So what we were able to do is we were able to write the concentration of this thing in terms of the concentrations of other things, right? So that's a key skill in being able to do that more complicated reaction mechanism problem I was mentioning before, where the second step in your mechanism is slow. So let's have a look. I think we're about to do that problem. It says writing the rate law implied by a simple mechanism. So it's a two-step mechanism, and here are the elementary reactions. It looks like it's first order in everything, only one of each things. But then here's the kicker. It says suppose also that K1 is much, much smaller than K2. That is the first step. Oh, is much slower than the second. No, we're still doing the easy type of problem. So that one is slow and that is fast. So this is just like what we saw before. So the slow step is the rate determining step, and the rate law for that step equals the rate law for the overall process. So the first thing they're going to get us to do is to write the balanced chemical equation. So we're going to add together our two elementary reactions, cancelling intermediates where we can, and collecting like terms. So what do we got here? It looks like HI is our intermediate, just the one intermediate. And then we're going to end up with 2 ICl, and then I2 and 2 HCl. And then we're going to check everything balances. So 2 hydrogens, 2 hydrogens, 2 iodines, 2 iodines, 2 chlorines, 2 chlorines. So that's my overall equation. So we've got the first part. Now I know that my overall rate is equal to the rate of step 1, which is going to be equal to K1, and then here, this is step 1 up here. So it's first order in H2 and first order in ICl. H2, ICl. And so there is my rate law for the reaction. So that was pretty easy. You don't need to put the K1, you can just put it as K. And then it says express the rate constant for the overall chemical reaction in terms of K1, K2, etc. And if necessary, the rate constants for the reverse reaction. Well, K in this case is just equal to K1. Yeah, see, K is just equal to K1. So that was easy. All right, so that was another example of the same thing. We have to eventually get one where we're going to flip the order, surely. No? Okay, we got lucky. Perhaps I'll go back and do an example where I just assume that the second step is slow and show you how to do that. So this one is about deducing information about reaction mechanisms from a reaction energy diagram. So let's have a look here. The reactants are higher in energy than the products. So that means that as the reactants got turned into products, energy got released, right? So that means that this is an exothermic process. Now, each one of these peaks here represents an activation energy barrier. It represents a transition state. And so we know that there is 1, 2, 3 elementary steps or elementary reactions in this mechanism. We also know that the elementary reaction with the largest activation energy is going to be the slowest one. So if I look at this, just kind of eyeballing it, I can see that in order from slowest to fastest, it's going to go step 1 has the biggest activation energy. Step 2 is a bit smaller. And then step 3 is a little tiny bit smaller again. So this would be the slowest of the steps in the mechanism. It would be the rate determining step. And then this one would be the fastest, right? So let's have a look at this. So does this reaction release or absorb energy? It releases energy because the products are at lower energies than the reactants. How many transition states occur during this reaction? That's just the number of peaks in your curve. 1, 2, 3. Could this be an elementary reaction? It can't be, because there are multiple transition states, right? An elementary reaction only has the one transition state. If you said this reaction could not be elementary, then how many steps are in the mechanism? Well, there are 3. If you said this reaction could not be elementary, then enter the number of steps in the mechanism, which is the... if you said the reaction could not be elementary, then enter the number of the step in its mechanism, which is rate determining. Well, it has to be the first one, because the first one has the highest activation energy, right? It has the highest activation energy. Okay, as promised, I'm going to go back here, and we're going to do a problem where the second step is slow. Okay, so what we're going to assume here is going to ignore that information there where it tells you that the first step is slow, and we're going to assume that the second step is the slow one, and we'll work through that. Okay, so what I'm going to do is I'm going to pretend that that's not there, and I'm going to pretend that this is fast and this is slow. So my balanced chemical equation, if you recall, was, I'm not going to repeat that, but we add the two together. It was this, that was my balanced chemical equation. All right. Now, what I know is that the second step which is first order in HI, that one there is my rate determining step, and the rate of that is equal to my overall rate. The problem is that this rate law has the concentration of an intermediate in it. It has the concentration of something that doesn't actually appear in my overall equation. And we can't have rate laws like that. Rate laws are of this form. the rate law for this overall reaction will be K multiplied by H2 to some power A multiplied by ICL to some power B. Now, because this is an overall reaction, not an elementary reaction, we can't assume that the orders will be 1 and 2. So the difficulty that we have is we have to figure out how to express the concentration of HI in terms of things that appear in our overall reaction, because they're the only things that we can actually determine the concentration of. So how are we going to do that? Well, what we have to understand is what happens when we have a fast step followed by a slow step. What is going to happen is this. These two products are going to be produced very quickly, but they're going to be consumed very slowly. In fact, the HCl isn't going to be consumed at all. That's just going to build up. And then the HI, because this second step runs so slow, will also build up in concentration. And what that means is that the concentration of these guys will build up, so the reverse reaction starts going faster and faster and faster. Meanwhile, the concentration of the reactants is getting consumed. So that ends up going slower and slower and slower. And eventually you reach that point of equilibrium where the rate of the forward reaction equals the rate of the reverse reaction. So the rate of the forward reaction for the first step becomes equal to the rate of the reverse reaction for the first step. And that's our key to getting an expression for the concentration of HI in terms of the reactants and products that appear in our overall equation. So the rate of the forward reaction can be written as K1 multiplied by the concentration of H2 to the power of 1 multiplied by the concentration of ICl to the power of 1. And how I'm getting that is just from the fact that in this elementary step or elementary reaction, there's one of each of those two things. Now, for the reverse reaction, it's going to be first order in HI and HCl. So that is going to be K minus 1 HCl HI. And then we do that little trick that we'd seen in the previous question where we reorganize this to get that expression for HI. So now that's going to be K1 H2 ICl divided by K minus 1 HCl equals the concentration of HI. Now the nice thing is everything in this term here, all of the chemical species there are present in our overall reaction. So what we're going to do is we're going to take this term and substitute it for the concentration of HI in our rate law, and then we're going to get a rate law that only has things in it that appear in our overall equation. So the rate for our overall equation is going to end up being K2, K1, K minus 1, and then we've got the concentration of H2 ICl on HCl. So this part of that is really just the other way of writing the concentration of HI, right? And then we've just got one more term, which is the concentration of ICl. So you put all of that together into kind of something that kind of makes sense, and you've got K2, K1 on K minus 1, and then we've got the concentration of H2 to the power of 1, the concentration of ICl to the power of 2, and then I'm going to write the concentration of HCl to the power of -1. So it kind of looks like a rate law. And what we should recognize is that this is just a collection of constants. So we could say that the overall rate constant for this thing is just equal to K2, K1 on K minus 1. So when we go back up here, it's similar to what we had before. All right. We've got the overall balanced equation. That just goes up into there. And then it says, write the experimentally observed rate law for the overall chemical reaction. Your answer should not contain any intermediates. So we discovered that it was first order, right? Where is it? First order in H2, second order in ICl, and then -1 order in HCl. And none of those things are intermediates, right? So first order in H2, second order in Cl2, and then -1 order in HCl. And then when I look in here, all of those things, H2, ICl, HCl, appear in my balanced overall equation. So I'm good there. I don't have any intermediates there. Now, what was my rate constant in terms of the rate constants of the elementary steps? It was K1, K2 on K minus 1. Right? And we had that at the end there. It was K2, K1 on K minus 1. All right. So, so that's tricky. It's not easy. So, make sure that you are able to do a problem of that type.